Good morning, children. This is 12th Physics, Unit 3, Magnetic Effects of Current and Magnetism. We are doing chapter number 6, Electromagnetic Induction. Today we are going to start with Faraday's laws. So let's begin with Faraday's first law of electromagnetic induction. So children, Faraday's first law, it tells us about the reason why EMF is produced in a coil. So here we can see, children, that here if we are having a coil and the coil is having about N turns. Now near this coil we have placed a bar magnet. So children, when we are moving the north pole of the magnet towards the coil, so the magnetic flux, the magnetic field lines that are passing through this coil, it changes. So what is changing, children? Magnetic flux is changing when you are bringing the north pole of the magnet near the coil. So due to the changing magnetic flux that is passing through the coil, an EMF is induced in the circuit. So your EMF will be produced till the magnetic flux changes. Once the magnetic flux becomes constant, means you make your bar magnet stationary, no more the current will be induced in the coil. So when you are moving the bar magnet towards the coil or away from the coil, the magnetic flux that will be linked with the coil will change and an EMF will be produced in the coil as long as the EMF keeps on changing. So this is your first law of Faraday's first law of electromagnetic induction. Now let's talk about the Faraday's second law of induction. Okay, so here children, as the first law told us about the reason that when the flux linked with the coil changes, EMF will be induced, right? Now this law will tell us about its magnitude. Okay, first law said EMF will be produced. Okay, how much? So this law will tell you about the magnitude of the induced EMF, right? So Faraday's second law says that the magnitude of induced EMF, it depends upon, it is directly proportional to the rate of change of flux linked with the coil. Means how fast you are moving, how slow you are moving, how fast you are bringing the north pole of the bar magnet towards the coil. So the rate at which the flux changes. So faster the flux changes, more will be the EMF that will be produced in the coil. So children, mathematically we can represent this as E is proportional to d phi by dt. E is the EMF and d phi by dt is, d by dt is rate of change of and phi is flux. So rate of change of. So proportional sign if we remove, a constant will come and that constant value is 1. But here children you will say, ma'am, that here we can see minus sign. Yes, here children minus sign is the indication for the direction. This minus sign is in accordance with the Lenz law, which we will be covering in the next topic, right? Now this is for one turn. If there is for one turn, the EMF produced will be this. But if there are n turns, then simple, multiply it with n. So E equals to minus n d phi by dt. Right, children? Now, children, if the resistance of the coil, this coil is having the resistance R, then according to Ohm's law, we can say I equals to V upon R. V is your EMF, right? Voltage. So E ho jayega, V ki jagah E. And if we substitute the value of E over here, then it will be minus n d phi by dt upon R. Now, if you want to calculate this is your magnitude of induced current. Suppose we want to calculate induced charge. So we know I equals to dq by dt. So if we replace I by dq by dt minus n by r d phi by dt, instead of I we are putting dt by dq by dt, right? So your dq will become minus n by r d phi. So children, here if you see the induced charge, it does not depend, the induced charge does not depend upon time, right? So it only depends upon the change in flux and not how fast or how slow the flux changes. That is only the induced charge. But induced current, it depends upon the rate of change of flux, is how fast your flux will change. Right, children? So this is a Faraday's second law, which tells you about the magnitude of the induced EMF. Now, we were talking about direction. Okay, magnitude is that much. But what about the direction? So, children, direction is given by the Lenz law. The direction of the induced EMF in the coil is given by the Lenz law. So before studying this law, we should be knowing some basic. That is, this is your coil, right? This is a coil. Now, if the direction of the current in the coil is anti-clockwise, see, direction of the current, you can see it is anti-clockwise. Then, according to the right-hand thumb rule, magnetic field direction will be outwards. It will be perpendicularly outwards of the plane of the paper. And this face, this side of coil will behave as north pole. This we should be knowing. If the direction is anti-clockwise, then the field direction, magnetic field will be perpendicularly outwards. And this side of coil, this face of coil will behave as north pole. Similarly, opposite with the other thing, that is, if the direction of the current is clockwise, then according to the right hand thumb rule, the magnetic field, see, you just curl your fingers along and along clockwise direction. So when you're curling your right hand fingers along anti-clockwise, you have to invert your hand, right? So your thumb points in the downward direction, that is into the plane of the paper. So the magnetic field direction will be into the plane of the paper, perpendicularly inwards. So that face, that front of a coil will behave as south pole, right, children? Now, here, what does Lenz law say? Lenz law says that the EMF that is produced will oppose the reason which is responsible for its production. Okay, what is the reason of production of EMF? Change in magnetic field, change in magnetic flux, change in magnetic flux, right, children? So if we see in this diagram, this is a bar magnet. So you are bringing this bar magnet near the coil. So as you are bringing the bar magnet near the coil, suppose initially the bar magnet is at rest. So as the bar magnet is at rest, the magnetic flux which is linked with the coil, it remains constant. There is no change. So no EMF will be induced, no current will be induced in the coil. But children, if we move the north pole of the magnet near the coil, the magnetic flux linked with the coil will increase. More number of field lines will pass through it, right? So magnetic flux will increase and it will produce an EMF. It will produce a current in the coil. Now, what should be the direction of the current? So children, according to Lenz law, the direction will be such that it opposes it. Now, what is the reason for its production? That north pole is coming towards it. So इसे oppose करना means वो चाहेगा कि north pole will move away. So if the coil wants the north pole to move away, then this phase of the coil should behave as north. This phase should behave as north. Then only north will repel, and this north will experience a force of repulsion and it will move away, right? It will move away. So for this phase to become north, what should be the direction of the current? So children, the direction of the current should be anti-clockwise. So the current that is induced in this coil because of the movement of this bar magnet will be in the anti-clockwise direction, right? Chalo, let's explain you. Let me explain you once more. Now, suppose what you are doing is here you are bringing or you are taking the north pole away from the coil, right? So as you are moving the north pole away from the coil, again the magnetic flux will change. The number of field lines which are passing will become less. So they are changing, right? So current will be produced in the coil, current will be induced in the coil. But what is the direction? Direction will be, it will oppose its cause. Cause kya hai? North pole moving away. So it will oppose this. It will try to bring the north pole towards it. So for bringing the north pole towards it, this phase of the coil should become south pole. And so the direction of the induced current, that is the current that is produced, should be clockwise. So because of this, clockwise direction current is produced in the coil. Okay, children, so this is your Lenz law. That is the direction of induced current, induced EMF is opposite to the change in the magnetic flux, right? And so we are getting a negative sign when we had done the Faraday's second law, that was E equals to minus d phi by dt. So here the minus sign indicated the direction of the induced EMF, that is, it is opposite to the reason of its production. Now let's move to children Fleming's right hand rule. This is a rule which will help us to find out the direction of the induced EMF, of the induced current, right? So for this, what we need to do, we need to stretch our right hand 3 fingers, that is the thumb, then the first finger and the middle finger perpendicular to each other, right? Then we have to place our first finger in the direction of magnetic field, and we have to place our thumb in the direction of the motion of the conductor, means in which direction we are moving the conductor, right? We are moving the bar magnet, so we are moving it in a particular direction, right? Then the middle finger will give you the direction of the induced current, the direction of the current that is produced in that conductor. Okay, for example, here we can see that we have placed a conductor, this is a conductor, in uniform magnetic field, and the cross indicates that the magnetic field is uniform and it is acting inwards, that is, it is perpendicularly inwards, right? And we are moving the conductor towards left. So children, what we will do, we will stretch our right hand 3 fingers, and the first finger will be in direction of magnetic field, that is into the paper, so inside the paper. So invert your hand downwards. Now the thumb towards the motion of conductor. Now conductor is moving towards left, so turn your thumb, first finger into the paper downwards and thumb towards the left. Then children, the middle finger points outwards, that is towards you, perpendicularly outwards. So that is the direction of the induced current, of the induced EMF in the coil. Okay, children. Chalo. Move to the next topic, the motional EMF in a current. Motional EMF means beta? Motional EMF means EMF which is produced due to motion. So as we know children that EMF is produced due to the motion of the conductor, it is known as the motional, EMF. Right? It is known as the motional EMF. So here we are going to calculate the magnitude as well as the direction of the motional EMF. So children, Here we are having the magnetic field B. As we can see, it's uniform magnetic field and it is represented with cross. So the magnetic field B is uniform and its direction is into perpendicularly in the plane of paper. It is inwards, right? Now we are going to place a U-shaped wire. So this is a U-shaped wire which you have placed in a uniform magnetic field B, which is directed into the plane of paper inwards, right? Now what we are doing, we are placing a conductor PQ on the U-shaped wire. So this forms a loop. So children, this forms a loop, and this rectangular loop is PQRS. This rectangular loop is PQRS, right? Now children, if we move the conductor with velocity v, we are moving this can move like this over this wire. Wire is at the bottom, right? It's stationary, and over the wire we can move the conductor, that is PQ. So suppose we move the conductor PQ with velocity v. So on moving the conductor PQ, the magnetic flux linked with the loop, that is PQRS, will change. And as the magnetic flux is changing, an EMF is induced in the coil, an EMF is produced in the coil, right? So that EMF, we know it will be given from Faraday's second law, that is E equals to minus d phi by dt. This we know. Now, suppose at time t it is moving, right? PQ conductor is moving with velocity v. At time t, the distance, that is RQ, is x and length of the conductor is L. Then what about the area of this loop PQRS? So area will be length into breadth, that is L into x, that is Lx, right? And we know that flux equals to B dot A, that is BA cos theta, where theta is the angle between the magnetic field B and the area vector A. Right, area vector A. Suppose we consider the back phase of this loop. पीछे की साइड अगर हम कंसिडर करते हैं तो उसका एरिया वेक्टर कहाँ होगा बेटा? पीछे की तरफ, perpendicular inwards. And the direction of magnetic field B is also same na beta, it is perpendicularly inwards. So angle between B and A is 0 and cos 0 is 1. So you will get phi equals to BA cos 0, that is BA, and instead of A we can put the area, that is Lx. So phi equals to BLx. Now this value of phi, if we put it over here, then d by dt of BLx. B is constant, magnetic field constant, length of conductor is constant. Yes, x is changing because we are moving the conductor PQ. So x will change. So it is dx by dt. Dx by dt, d is what? Displacement, right? And dx by dt, rate of change of displacement is velocity. So E equals to minus BLV. So this is the magnitude of the EMF, that of the motional EMF, right? And here we are having, or rather, let's find out the direction. So children, the direction will be found out by Fleming's right hand rule. So what you need to do, stretch your three fingers. Yes, first finger in the direction of magnetic field. So first finger magnetic field means inwards, नीचे की तरफ कर दो बेटा, right? Then thumb in the direction of motion. So in which direction you are moving? So V is towards right. So turn your thumb towards right. But the first finger should be downwards only. Then children, the middle finger, as you can see, it is pointing towards from bottom to top, that is from Q to P. Yes, from Q to P, from down to up, it is pointing in the upward direction, right? So the current that is produced will be in the upward direction. Okay, so the current that is produced will be in this direction, and that is I. Okay, beta. Chalo. This is the direction. This is the magnet. Now we are having a special case. That is, suppose we are moving the velocity. Suppose we are moving with velocity, means velocity is not perpendicular. Okay, just one more thing I forgot to tell you, that here the conductor, it will behave as battery, because here current is produced from Q to P. So the current enters the circuit from P. So this is at higher potential and this is at lower potential. So this is the current, that is I, that is produced in the circuit from Q to P. Right, P will be at higher potential and Q will be at lower potential, because we know that in a circuit, from the battery, from the positive terminal, the current flows through the circuit to the negative terminal. So here also, children, current is flowing from P through the circuit to Q. So P is at higher potential. Now, special case we are discussing. In the special case, children, suppose the conductor is not moving perpendicular to B. Here the conductor was moving, velocity was perpendicular. But suppose it is making some angle, theta. Then children, what will be the EMF? Then what we are going to do? We are going to resolve the velocity component into two. That is, one is the horizontal component, V cos theta along B, and other is the perpendicular, that is along the other perpendicular to it, that is V sin theta, that is perpendicularly outwards. That is perpendicular to B, right? Now children, as V cos theta and B, they are along the same direction. So no induced EMF, it will not produce, because no magnetic field lines would be cut by this V cos theta component. So children, the whole sole component which is responsible for the change in magnetic flux is V sin theta. So here in this case, V sin theta is the component which is responsible for the induced EMF. And so here we will replace V with V sin theta for this special case. But for your motional EMF, the magnitude of EMF is E equals to minus BLV. And minus sign is in accordance with the Lenz law. Right, children? Now let's talk about the rotation of a rod in magnetic field. So children, here, if we rotate a conducting rod, this is a conducting rod. If we rotate this rod perpendicular to B, then what amount of induced EMF will be produced, right? So we will calculate the magnitude as well as the direction for the EMF produced when we are rotating a rod in magnetic field. So first let's talk about the magnetic field B. So magnetic field is represented by cross. Cross means it is inward into the plane of paper. It is perpendicularly inward, that is into the plane of paper, and it is uniform, right? Second thing, here we are having a conducting rod of length L, and we are rotating the rod with angular velocity omega. So the angular velocity omega, the length of the conductor is L, right children? And with this angular velocity omega, the area that is covered by this rod is, sorry, area not, it's angle. The angle covered by the rod is theta. The angle covered by the rod is theta. Suppose we talk about when the rod covers one complete circle, for one circle, right? For one circle, children, the angle will be 2 pi, right? And the distance that is covered will be the area that is covered is pi r square, but यहाँ पे radius कितना है, length of the conductor, right? So it will be equal to pi l square. This is what area, this is what angle, right beta? This is for one circle, one complete circle, right? This is the angle, 2 pi angle के लिए. But for unit angle, right? For unit angle, for unit angle means for angle 1 डिग्री के लिए 1 डिग्री के लिए एरिया कितना हो जाएगा पाई एल स्क्वायर अपॉन 2 पाई सिंपल मैथ्स करते हैं ना 2 पाई के लिए एरिया पाई एल स्क्वायर तो 1 डिग्री के लिए कितना पाई एल स्क्वायर बाई 2 पाई बट वी आर कवरिंग एन एंगुलर डिस्प्लेसमेंट ऑफ थीटा तो थीटा के लिए कितना बेटा सिंपल जस्ट मल्टीप्लाई इट विथ थीटा so this is unitary method which we are following so it will be your pi will get cancelled so it will be L square theta upon 2 right children so this is your maths unitary method so in angle theta the area that is covered is L square theta by 2 this is the area that is covered for the angular displacement theta. Now we want to calculate the EMF. So EMF we know that is E equals to minus d phi by dt. But phi is B dot A that is BA cos theta. Here the angle between the magnetic field B and the area vector A that is they are along the same direction. If you consider the back face of this of this rod it will be perpendicularly inwards and magnetic field B is also perpendicularly inwards right so angle is theta and if you consider the front face of this rod then it will be perpendicularly outwards and magnetic field B is perpendicularly inwards so the angle will be 180 and cos 180 is minus 1 so we are only calculating the magnitude so children minus sign we will not consider and so we are taking the angle between B and A to be 0 so cos 0 is 1 and your phi will be BA but value of A we will substitute from here so it will be instead of A we will put L square theta by 2 so phi that is your flux will be B L square theta by 2 now EMF is minus d phi by dt so d by dt of B L square theta by 2 now let's see how many terms are constant children so here children B magnetic field constant length of conductor constant yes angular displacement theta will change though d theta by dt that is rate of change of angular displacement is angular velocity so omega so children this is the magnitude of the EMF that is produced due to rotation of a rod in magnetic field okay so here we are having this is it children for the rotation of a rod in magnetic field. Now, if we talk about the direction, children, come on, let's use Fleming right hand rule. Stretch your 3 fingers, right? First finger will be in the direction of magnetic field, so put it straight inwards, right? Now, thumb, you are moving the rod in the upward direction, right? The rod is moving like this, so upward direction. So, thumb will be pointing upwards, so straight up, right? Then the middle finger gives you the direction of induced current. So, middle finger is pointing towards left. So, current will be produced from P to Q. Current will be produced from P to Q, right? And this current, suppose if we connect over here, if we connect a wire like this, so current कहाँ से निकलेगा बेटा? Q में से निकलेगा, circuit में से जाके फिर वापस P में आएगा. So the direction of the current is from P to Q, but O will be at higher potential and P will be at lower potential. So this is the direction of the induced EMF due to the rotation of the rod in magnetic field. Now children, let's talk about the rotating disc in magnetic field. That is the EMF that is produced when we are rotating a disc in magnetic field. So children, consider a disc of radius L which is placed in magnetic field B. Your magnetic field B is uniform and it is perpendicularly inwards. Now let us rotate this disc with the angular velocity omega. We are rotating the disc with the angular velocity omega. Now when it moves by cutting the cutting the magnetic field lines. That is, on the movement it induces EMF. This EMF is produced between the circumference and the center of the disk, right? So here the frequency is F, that is frequency is the number of turns in 1 second, right? And we know the omega equals to 2 pi F, right? The angular velocity equals to 2 pi F, and let the area of the disk be A. Now children, we know phi, flux is B dot A, that is BA cos theta. Now the angle between B, magnetic field B is inwards, and if we take the back face of this disk, पीछे की side ले, then the area vector will be inwards, that is along the magnetic field B, and that will be 0, and cos 0 is 1, so the flux phi is BA. We want to find EMF, induced EMF. EMF is minus d phi by dt. Minus sign is in accordance with Lenz law, that is direction. So we can ignore this because we are finding out the magnitude. So E equals to d by dt of, instead of phi we will put BA, right? B is constant, so that will come out of differentiation and you will get dA by dt. So children, dA by dt is very interesting here. dA by dt, it is the rate of change of area, how much area it is covering. So how much area it is covering, this is rotating, so how much area it will cover, it depends upon the number of rotations, it depends upon the frequency, right beta? So this rate of change of it depends upon two things. Firstly, it depends upon the area of the disk, and secondly it depends upon the frequency. In one turn, the area that it will cover on one rotation is A. But if there are F rotations, then how much area? That is AF. So that is the area which is covered in the total motion. So children, here dA by dt is rate of change of the area covered. That will be equal to AF. So simple, dA by dt को replace कर देंगे AF से, and this is the formula of induced EMF, which is equals to E equals to BAF. Now we can substitute the value of A as pi L square. Pi R square नहीं, क्योंकि L है उसका radius, so it is pi L square. F को अगर यहाँ से subject of formula बनाते हैं, F equals to omega upon 2 pi. Pi cancel and your induced EMF is equals to half B omega L square. So children, this is the magnitude of EMF produced when we are rotating a disk in uniform magnetic field. Now let's talk about the energy when we are having a motional EMF. Does it obeys the energy law? Let's see children. So this already we have discussed that as we place the conductor in magnetic field, and if we move the conductor, then induced EMF will be there, right? Now suppose you are having a conductor over here and the length of the conductor is L, and you are moving the conductor in uniform magnetic field B, right? So here this we know, that is E equals to BLB. This we have derived. Now from Ohm's law, if you want to find out the current, that is I equals to E by R, that is I equals to V by R, that is E by R. So put the value of E, then it will be BLV upon R, where R is the resistance of the PQ conductor. और इसका जो resistance है ये wire का, वो हमने neglect कर दिया. That we are making it as 0. So R is the resistance of the conductor PQ. So this is the induced current in the loop. Right children? Now let's talk about the direction also. We can talk about the direction. So from Fleming's right hand rule, we will come to know if first finger is in the direction of magnetic field B, that is inwards, अंदर की तरफ, right? Then thumb is in the direction of motion. In which direction we are moving? Towards left. Then you can see that the middle finger is in the direction that is downwards. That is the direction of the induced current. So current कहाँ से produce हो रहा है? P से Q, right? And as the current is entering from Q to the circuit, through the circuit to point P, So Q is at higher potential and P is at lower potential. This we have done in the previous topic. And children, we also know that when we place a current carrying conductor in magnetic field B, it experiences a magnetic force. अगर आप magnetic field में current carrying wire को रखते हो तो उसके ऊपर force लगता है, right? And that force will be experienced. Now your current is produced in PQ and PQ is in magnetic field B. तो PQ के ऊपर भी तो एक force लगेगा, that is magnetic force, and its value we know, that is magnetic force is IBL sine theta, where theta is the angle between the current I and magnetic field B. Now current direction of between the current is in this direction, magnetic field B is inwards, so they are perpendicular to each other. So sine 90 will become 1. So here children, you will have FB is equal to BLB upon R, and here you are having sine 90 will be replaced by 1. So we have substituted the value of I over here, right? So this is the formula for force. This is the formula of magnetic force which will be exerted on this current carrying conductor PQ. इतना magnetic force उसके ऊपर लगेगा. What about the direction of this magnetic force? So we remember we had used Fleming's left hand rule for magnetic force direction, right? There the first finger was in the direction of magnetic field B. Magnetic field B inwards है तो अंदर की तरफ कर दो. Middle finger was in the direction of current. तो current तो कहाँ से जा रहा है? From P to Q, that is downwards. Then you will see that your thumb, left hand thumb is facing in the right direction. That is in the direction, this is the direction of the magnetic force B. Okay, so children, this is the direction of magnetic force B. So इतना फोर्स उसके ऊपर लगेगा कि वो इसको पुश करेगा. बट अगर हम चाहें, इफ यू वांट दैट दिस PQ should move towards left only with a constant velocity of v, then we have to also apply some force ना, हम भी तो कोई force लगाएंगे, and that force will be exactly equal to the magnetic force. So external force which we will apply because we want the conductor to move towards left with a constant velocity of v will be equal to the magnetic force, which is equal to this. Now let's calculate the mechanical power to move the conductor with the velocity v towards left. So mechanical power, we know it is force into velocity. So force into velocity is this, right? This is the mechanical power. Now if we want to talk about electrical power, so we know electrical power is I square R. So I square R, if you put value of I from here over here, you'll get this. Now if you compare mechanical power, electrical power, they are same. It means that the mechanical energy which we are providing, हमने force लगाया ताकि conductor move करे, that is converted to electrical energy, and finally it will converted to heat energy. So here it obeys the law of conservation of energy. Now children, let's proceed towards the next topic, that is rotating coil in magnetic field B. So when you are rotating a coil in magnetic field, then also EMF will be induced. So we are going to calculate the magnitude and the nature of the induced EMF, and we will also calculate the maximum value of the induced EMF. So children, here what we are having? Here we are having a uniform magnetic field B. As you can see, this is uniform magnetic field of strength B. Uniform magnetic field means the magnitude of magnetic field B is not changing with distance or time. Right. Now suppose here we are having a coil. So you can see this is a coil and we are going to rotate the coil in magnetic field. Now the coil is having N turns, right? And we are moving the coil, we are rotating the coil with angular velocity omega. Suppose let in time t, the coil gets rotated with angle theta. Suppose t time में theta angle का rotation होता है. Right? So theta is the angular displacement in time t. So angular velocity is what? Angular velocity is angular displacement upon time. So omega equals to theta by t. Now we know flux phi equals to B dot A. that is BA cos theta, where theta is the angle between the magnetic field B and area vector A. So the angle between the magnetic field B and the area vector A, that is equal to theta. So that we will put it by theta. And from here, if we make theta subject of formula, theta equals to omega t. So this value of theta we will put over here. That is phi equals to BA cos omega t. Now we know flux is according to Faraday's second law. We know the flux E equals to minus d phi by dt, but there are n terms, so it will be minus n d phi by dt. Minus sign is in accordance with Lenz law. So if you find magnitude, you can remove minus sign, no problem, right? So if you put the value of phi from here in this, so it will be BA cos omega t, right? Now what is constant? And B is constant, A is constant, that will come out, and you will do the differentiation of cos omega t. So beta cos ka differentiation we know it's minus sin omega t, and omega का t का differentiation करोगे तो omega आएगा. So it is minus sin omega t into omega. Minus minus दोनों will become plus, and so you will have NBA sin omega t. NBA sin omega t. Now, if you want children this value to be maximum, then maximum value of sin will be 1, right? So, sin, if we make it 1, that will be the maximum value of the EMF that is induced in the coil. So, for that, the theta will become 90, right? So, this will become 1, and you will have the maximum EMF as NBA omega, right? So you can write this equation as, इसकी जगह E0 लिख सकते हैं, इसकी जगह E0 sin omega t. So this is the magnitude of induced EMF in a rotating coil in magnetic field.